Good morning. Here we are for the first lecture of CENG 3325, Structural Analysis. This is going to be the first video in a new series of videos that I'll be recording in the spring 2018 semester. These are recorded live in our structural engineering classroom here at UT Tyler. And we'll be going, my plan is to create a series of videos capturing lectures for the entire semester's course. So let's begin. This is going to be part one of lecture one. So for this part of the lecture, I would like to do a bit of review over shear and bending moment diagrams. So my objectives for our first lesson here today will be to go over internal forces in members, second to discuss support conditions, and then look at determinacy and stability. And I think I'll have a part 1, 2, and 3 covering each of those. So let's look at internal forces. Now, hopefully most of y'all are familiar with this from statics and from mechanics materials. I know if I taught you statics and mechanics materials, or either of those, you're very familiar with them. But I see some new faces here, so I don't know if you've all seen all of this before. So it's good to do a bit of review. So internal forces review. Internal forces review. And let me make sure we're rolling. And we are, so we're good. Okay. Internal forces review. Basically I want to discuss what is shear, what is bending moment, what is axial force, all of these things, etc. So, essentially, there are 3 internal forces can exist in a member. At least 3 main ones. Torsion can exist within a member, although we don't typically deal with that in structural analysis, because we're typically talking about frames, that sort of thing, usually 2D frames. 3 internal forces can exist in a member. And this is, so and these 3 are going to be axial force. And so this is definitely a bit of a review from mechanics materials, maybe from statics. Axial force, shear, and moment. And I'll discuss each of these. Axial force, shear, and moment. So axial force, this is going to be your tension and compression longitudinally. And tension is going to be positive and compression negative. Compression negative along longitudinal axis. And I think I'll draw these down below. Longitudinal member axis. And I apologize in advance for my terrible handwriting. So for example, if I were to, let's look at a just generic member. And it could be a beam, it could be a column, but I'll just go ahead and draw it as a beam. So let me just draw a simply supported beam. And let us imagine that I cut it right here and then analyze or look at the forces inside this. So I have my member here and I have my cut. And I have the other end of the member here and it's cut. So first, let's look at axial force. Again, it's going to occur along the longitudinal axis, and the longitudinal axis, again, would be something along the length of the member, like this. And so I could call this, usually when I'm labeling these, I call this N for sort of a normal force, an axial force. Like this. N, N. Next, I have shear, which is a force, not a moment, but a force transverse to the member, or to the member axis. Transverse to member axis. Cell phone's going off, lovely. Anyway, and so that's going to be recorded for posterity. Anyway, so then we have shear, which now I forgot, what variable do we use for shear? V, very good. Yeah, I'm just so forgetful sometimes. So we have a V here and a V here. And then finally we have moment, which is going to be bending about the transverse axis. Although you can also have weak axis bending, which would be about, well, I guess no, it's always about a transverse axis. Bending about the longitudinal axis would be torsion. And you can have strong and weak axis bending. And I think I'll talk about that in a bit here. Strong and weak axis bending. Okay. So again, these are our three main internal forces, but I do have some notes on this that I'll cover on the next slide. And I am going through this fairly quickly, but this is because this is a review for mechanics, materials, statics, etc. Okay, so I need to talk about sign convention. What is a sign convention? Well, obviously, a sign convention is a trade show of the billboard advertising agency or industry. No? Okay, that's a really bad joke. Get it? Sign convention, billboard convention? No. Oh, it is Monday. Or, no, it's not Monday. It is Thursday, the first day of class.
8 a.m.
8 a.m., yes. So let's look at sign convention. Let's look at sign convention. So we need to define positive shear and positive moment. I want to define positive shear and positive moment. Now, this is always something that gets students or trips students up because they see an upward arrow, they want to call it positive. They see a downward arrow, they want to call it negative. But what makes positive shear and moment, and also with moment, they see a counterclockwise arrow, they want to call that positive. They see a clockwise arrow, they want to call that negative. But when you draw a free body diagram using method of sections in a beam, defining positive and negative shear and moment is a bit more complex. So I'm going to draw two elements, here and here. Just two elements, and this would be something like, this would be like a section of the beam. Like imagine if I cut out a section of the beam, a small length of the beam, and then looked at the forces herein. So here, positive shear is going to have a upward arrow on the left and a downward arrow on the right. This is simply a sign convention. This is just something that we choose to define as positive. We can define the other way as positive as well, but just by sign convention, we refer to this state as positive. So, and what if you have a positive arrow on the right and the left? That's impossible. And the reason for that is unless there's a point load, and this wouldn't matter for, even a point load wouldn't matter for this, because this would be when I draw this out, basically what I'm drawing out is, if you remember from calculus, a differential element. I'm drawing out a small dx, a small differential element, and so point loads aren't going to be occurring across a differential element. And so when we're talking about an element that small, we're basically saying the force on the left is equal to the force on the right. This thing has to be in equilibrium. And then positive moment is going to have a clockwise arrow on the right, on the left, and a counterclockwise on the right. And basically what this is this produces positive bending. If you remember from statics or other courses, or mechanics and materials, positive bending is defined as bending that makes a nice little smiley face. And the reason for this is, so if something is curving downward, basically mathematically we would refer to this as concave up. If a beam's curvature is concave up, we call that positive bending moment. So we do that for a couple of reasons. One, it works nicely with, we use that sign convention for a couple of reasons. One, it works nicely with mathematics. Concave up is positive bending, that works very nicely. Also, from the point of view of civil engineering, which do you think you encounter more often, positive or negative bending? Generally positive, yes, because usually when the main reason we use beams is to resist gravity. We use them to gather loads up to resist gravity. Weight, live loads, self-weight, live loads, dead loads, that sort of thing. And although we haven't learned how to work with load combinations yet, we will. Now, there are definitely times where you can have negative bending in beams, especially when you have a continuous beam that passes over multiple spans. Like imagine if you have one beam that passes over a series of columns, and let me just draw this out. That'd be a bit better, I think. For example, if I have a whole bunch of columns, a series of columns, and I put a single beam on top of this, and I load it like this, I put a distributed load, say, if I put a distributed load right on the middle, let's look at how this is going to bend. This thing is going to go into positive bending, but these are going to go into negative bending. So especially in the case of continuous beams, it's very easy to get negative bending. But for, at least for simply supported beams, or for most of our cases in general civil engineering, we are dealing with beams bending this way rather than this way. So this is positive bending. And I do want to refer to something on the previous slide to remind us of something that I kind of glossed over that I want to look at here. On this cut, there is something to keep in mind. Oh, first I need to label my moments. I lost my moments here. M and M. And what do you notice on this drawing between this side and this side? Huh? Yes, very good. Opposite directions, matching pairs. Basically, this is just Newton's laws. For every action, there's an equal and opposite reaction. When we look at internal forces in a beam, in a column, things like that, wherever you have a cut, there is going to be an equal and opposite force. And so we can use this different ways. Sometimes we look at a cut somewhere along a member. Sometimes we look at a cut at a joint. But any time that we cut a member, we're going to have equal and opposite force pairs. And so, and that's going to be very critical to this, and this is really a foundational element of the entire course. A lot of the material that we'll go through this semester is going to be using this idea of equal and opposite force pairs. All right, so we have that. And again, this is, I just want to mention this and this are on differential elements. And I promised I would mention something about weak axis and positive axis bending. And remember, I defined moment as bending about the transverse axis. But if you think about it, if you think in 3 dimensions, a beam can have, or a member has 2 different transverse axes. If I have a beam like this, if the longitudinal axis is here, there are going to be 2 different transverse axes. There's a vertical transverse axis up and down here, but then there is a horizontal transverse axis, which is into the page here. So I'd like to define the difference between strong and weak axis bending, although in this course we're going to deal primarily with strong axis bending, especially the only way you can really end up with weak axis bending generally is if you're dealing with some sort of 3-dimensional problem, but we're going to stick mainly with 2D frames, but maybe a little bit of 3D here and there. So let's look at strong versus weak axis bending. Okay, so like I said, there can be a moment is bending about an axis transverse to the longitudinal axis. However, there are two transverse axes. So therefore, there are two transverse axes. All right, so now, again, if I have my beam, something like this, let me do maybe the axes in orange. This would be my longitudinal. And then let's say into the page here, maybe I'll do the little dot with a circle around it to indicate into the page. This would be strong axis. This would be strong axis. And bending about this axis would be weak axis. At least generally. Depends on how you orient your beam. But generally we put the strong axis to resist bending about this. Because if you think about this, if you're having trouble visualizing this, so first let's imagine some supports here. Nice pin and roller, and we will review this. But if you imagine this, imagine the right-hand rule. If you put your thumb along this axis, you can imagine the beam bending like this. If you do the same thing with the vertical axis, the beam itself would be bending into or out of the page. Now, let's look at this from the cross-sectional point of view. If I take this and look at its cross-section, let's say this is now it could be, the actual beam could be any number of things. It could be a rectangular section, it could be made of steel, it could be made of concrete, it could be made of wood. But let's say it's a simple steel W section because I like steel. And if you remember your statics, if you remember, especially if you remember your mechanics and materials, you'll be able to tell me how a W section works. It works by, can you tell me, what is the logic behind a W section? Why do we design it? Why do we lay things out like that? Exactly, yes, very good. The area moment of inertia, very good, especially on the strong axis. The entire logic, and we'll see this more through the semester, and you'll see it in steel and concrete design. The entire logic of W shape is to get as much area as far from the neutral axis or as far from the centroid as possible, because that is what gives you your bending moment capacity. So you want lots of area far from your neutral axis, and that's what creates your bending moment capacity. So that is really why a W section is laid out the way it is. But back to this axis. Question? Yeah. Transverse definition means perpendicular. So basically, but good question. Longitudinal, that's fairly straightforward. That means along the length of a member. Transverse would simply mean any axis that is perpendicular to that. But yeah, good question. That's just a term from geometry, engineering, general term, etc. So I would usually call this the x-axis, and then at least we do in mechanics and steel and concrete. And I would call this the y-axis, except that should probably go right through the center of the beam instead of, off kilter a bit there. But x, this would be the strong axis. And y, this would be the weak axis. So we can see, because of the amount of area further from this axis of bending, this W shape will be much stronger in bending about the x-axis than it will about the y-axis. So that fundamentally is the difference between strong axis and weak axis bending. Any questions on that? All right, so that's the basic difference there. Next, I just want to give a few notes on shear and bending moment diagrams. So, shear and bending moment diagrams, next major topic here, but building up on our discussion of internal forces. And I do have a whole series of videos on these, and we will talk about this more in greater depth, especially more by integration later in the semester. but I do want to give a brief introduction to it here because your first homework actually covers these. Shear and bending moment diagrams. So let's describe what these things do. These illustrate the internal forces. Including, but mainly, actually I should say internal shear and moment. We usually don't put axial force on these. The internal shear and moment, let's see, along the length of a beam. And again, I will cover in greater detail later in the semester. I just want to give a brief introduction here as a review. Later in the semester, especially via integration and more advanced cases. So you can cut and then solve for forces as a function of x. There's basically three methods. There's the method of sections, where you cut and solve for forces as a function of x, and then plot them. Let's see, you can also, let's say, solve by integration. We're going to spend a lot of time on this one because it ties in nicely with our discussions of deflection later in the semester. Solve by integration, where you use boundary conditions and such. You start with the distributed load, and then you solve for boundary conditions, that kind of thing. And then you can also use inspection. And then solve by inspection, just applying some generic rules here. But if you need a review of that, please feel free to see my mechanics materials review on this site here. Okay. I will do a brief example of doing one of these by inspection. All right, here. V&M by inspection example. Let's see, and the basic idea of this is based on the area under curves. So let's say this is given. We have a beam, a nice simply supported beam. And let's say we have a nice simply supported beam with points A and B. And maybe I have two loads on here. I have a 10 kip load and an 8 kip load. And the dimensions on here are going to be 4 foot, 6 foot, and 4 foot. All right, so the first thing I'm going to do is draw out a free body diagram. So all this is given, and I might as well do this right and proper and use the whole given, find, etc. format. Find the V&M diagrams for beam AB. The whole shear and moment diagrams for the beam. So I'm going to start with a free body diagram, and I want to do this on the next page because I like writing my, if I can, I like writing my shear and bending moment diagrams underneath a free body diagram because it makes everything nice and lined up. Okay. So, although, yeah, that's fine. So first I'll get the free body diagram. And I'm going to have two forces here, or two support forces. Let's see here. Or two reaction forces, I should say. And my two applied point loads. So I have my 10 kip force and my 8 kip force. And I don't know what you've been taught in other courses, but hopefully, I don't know if they teach you this in the mechanical engineering mechanics materials, but if any of you are unfortunate enough to have that. But anyway, if you're not familiar, a kip is what? 1,000 pounds. Hopefully everyone knows that by now. Hopefully, I know if you had me for statics or mechanics material, I definitely pounded that into your heads. But you never know where people are coming from. So if you're not familiar with that, a kip is 1,000 pounds. So we have this, and then we also have an AY and a BY. And truly, we would have if I were doing this proper, I could label an AX, although because we have no horizontal forces applied to the beam, we know that AX is going to be 0, so I'm just going to leave it off for now. So my first step is, of course, going to be to find the reactions AY and BY, and the simplest way to do that is just going to be by a balance of moments. So I'm going to say the summation of moments about point A, counterclockwise positive, equals 0. So just balance of moments, that's going to be negative 10 kips times 4 feet. And then let me go ahead and label some distances again. This was 6 feet and 4 feet. Actually, you know what? I forgot. Wait, why is this? It was negative because this is going down, right? But it's going down. It should be negative, right? Oh, because why? Yes, opposite my sign convention. Good. Yes. Gotta remember what positive moment is. Remember this? This is statics. We're bringing back statics. Isn't this fun? Isn't this fun at 8 a.m. or 9 a.m.? Of course, this is a measured from point A. This 10 kip force is going to produce a clockwise moment. Therefore, I've added a negative sign to my balance of moments. Then minus 8 kips times the total distance, which is going to be 14 times, that looks like 10 feet. And then plus BY, this one will be counterclockwise, therefore positive, times the full distance of 14 feet. And this produces a BY. If you solve that, I get that BY is equal to 8.571 kips. 8.571 kips. Then to get AY, I can simply do a summation of forces in the vertical direction. So a summation of forces in the vertical direction, upward positive. Upward positive, if I can manage to write legibly or semi-legibly. Upward positive. I don't always write that, but just for clarity this time. Must equal 0, and therefore I can simply say negative 10 minus 8 plus 8.571, and then plus AY equals 0. So therefore AY is equal to 9.428 kips, if I mathed that correctly. 9.428 kips. So we have our reactions, and now I can create my shear and bending moment diagrams. And what I'm going to do is I'm going to use the method of inspection. And the method of inspection, again, is based on the idea that is based on an area principle, where the change in between 2 points, the area under the distributed load diagram will be equal to the change in the shear diagram. And the area under the shear diagram will be equal to the change in the moment diagram. So for example, my shear here, let's see. Now I don't have any distributed load on here, so I don't have any area to take into account. Instead, what's going to happen is, immediately, and this is going to be in kips, immediately, right at the left end of the beam, I have a point load or a reaction that's going to cause the shear to jump up to 9.428 kips. And as I often like to do, I like to sort of sometimes draw some what I call trace lines when I'm doing these, especially on the board and even when I'm doing them on paper. These lines are serve no purpose other than just keep everything in line. These do not indicate any specific loads or anything. They're just something to keep my everything lined up, or sort of lined up. That one kind of veered off to the left there. So do we have any distributed load between this point and this point? No. So what's going to happen to the shear diagram? It's going to be horizontal. Yes, very good. There is no applied load between those locations, so the shear diagram is just going to be constant. Then I have a point load, a downward point load, that's going to cause the shear diagram to drop, and it's going to drop by 10, and that'll cause it to drop down to negative 0.572. Negative 0.572. Then there is no load between here and here, no applied load, so it's going to remain constant. Then here there will be a secondary drop, and this will be dropped down to this will drop down by 8 to negative. If I look at negative 0.572 minus 8, hey, what do you do? I get negative 0.571 or 0.572 within rounding error there. And then it will pop back up here from the point load at the right. And this would be negative 8.571. I have in my notes, that's probably just a little bit of a rounding issue. So in terms of signs, this is going to be negative, this is going to be negative shear, this is negative shear, and this is positive shear. And that is our full shear diagram. You can see these don't have to be fairly complex. Usually when I ask you to do a shear and moment diagram, I'm basically asking you to create what is essentially a sketch. And then M, let's look at the moment. Here. Now we are going to have some areas. And I'm going to label this M. And the units are going to be in kip feet. The units will be in kip feet. So what I need to do is I need to find the area under each of these things, because again, the area under the shear diagram is going to be equal to the change in the moment diagram. And so let's just get the areas of these. I'm going to get the area of this, this, and this. The first region, the area is 9.428 times 4, and this is going to be 37.71. That's for the first box. For the first region, the area for the second region, negative 0.572 times 6, and this is negative 3.432. And all of these would be in kip feet. And then the third region, negative 8.571 times 4, and this is negative 34.28. Negative 34.28. All right, so, don't want to bounce forward like that. Okay, so I know that between here and here, first of all, what is my moment going to be on the left end? Why? Why? It's true, it's 0, but why? Why is it 0 on the left end? Huh? Exactly, it is supported at a pin. So anytime we have an end pin or an end roller, we know that at that location, the moment has to be 0. Because at that location, the only way you can have an end moment at the end of a beam is if you have a fixed support. And we'll discuss that more in a bit. So I know that between here and here, the moment is going to increase by 37. Again, it is very important to keep in mind that the area does not give you the value, the area under the shear does not give you the value of the moment diagram. It gives you the change in the moment diagram. This is sort of that fundamental theorem of calculus stuff. And we will talk about this more later in the semester, but I just want to give you a brief introduction to this for homework and such. We'll go more through I'll have you working through solving shear and bending moment diagrams, especially by integration, later in the semester, especially when we get because I want you to be able to work with deflection by integration, that sort of thing. But, so I know here, it's going to be at 37.71, because again, I know that it's going to increase by 37.71, and since starting at 0, it's going to end up here. Now the question becomes, what kind of curve do I connect these 2 points with? This is going to be a linear function because we know there is an integral relationship between these things, and the integral of a constant value function is a linear function. So very good, yes. So I know from here to here, it's just going to be a straight line. Then I know from here to here, it's going to drop by negative 3.432. And if you subtract those two, you will get approximately 34.28. And by the same logic, this is going to be a linear function. And then this will also, hey, what do you know? It'll come back down to 0 with a drop of 34.28 here. And this whole thing is linear. And the whole thing is in positive bending. Now I know you can't tell from my terrible drawing here, but yes, this is a linear function, so linear throughout. Linear throughout. All right, any questions on the basics of internal forces and shear and bending moment diagrams? As a reminder, we will work through this more in the later parts of the semester, but this was just a brief introduction. Any questions on this before we continue? Okay. All right, I think I'm going to stop the lecture, this portion of the lecture here, stop the recording, and do this as a part 2.